Welcome back. So we're in the middle of talking about the mutual repression switch, and let me just remind you what the architecture of that switch is. So we thought about this in a previous vignette. The idea is that we have, as you can see here, we have repressor 1, and it actually represses gene 2. Gene 2 produces a repressor that represses gene 1. So that's the concept of the mutual repression switch. What we argued on the basis of our null clines and looking at the mathematics of the fixed points is that there are three fixed points in the case where the rate of transcription is large, and we argued that, and I'm going to prove this later, that two of those fixed points are stable and one of them is unstable. And what I want to do now is I want to actually think about the fixed points themselves. So that's the ambition for now. So what you can see in this box in the top is the rate equations describing the time evolution of the two repressors. And what I'm going to do in order to do my analysis of the nature of the solutions is I'm going to recast these in dimensionless form. So first of all, I'm going to define two dimensionless concentrations, U and V, and they're defined as you see here. And I'm also going to define a new time scale. Maybe I'll call it tau, which is equal to gamma times t. And if I write things in this language, then what I find is that du d tau is equal to minus u plus alpha over 1 plus v squared, and dv by d tau is minus v plus alpha over 1 plus u squared, where, and we've already defined tau, where alpha is defined as r over gamma kd. Note the units here. R has units of concentration per time in the original equations, which you can see up here. That's concentration per time. So R is units of concentration per time, gamma is per time, and kd is concentration. And so the net result is that this is a dimensionless variable alpha, which tells me something about the strength. So what we're going to do now is we're going to explore the fixed points. And in case 1, what I want to do is I want to think about the case where alpha is much, much greater than 1. So this is the large R over gamma kd limit. And what we're going to do is we're going to start out by assuming that U star is much, much less than 1. The fixed point, so I'm using the star notation to signify fixed point, and I'm saying we're in the switched state where U star is very small, and that better imply that V star is large. So let's just check that out. What we see here is that if we write down in steady state what V star is, it's alpha over 1 plus U star squared, but U star is small by assumption, and therefore V star is of order alpha. And now we can compute what U star is. So U star is equal to alpha over 1 plus V star squared, which is approximately equal to alpha over alpha squared, which is 1 over alpha. Why is that? Because alpha is much larger than 1, and so 1 plus alpha squared is going to be dominated by alpha squared alone, and so that's what leads to our final result. So here we found that V star is alpha, so V star is high, and U star is low, 1 over alpha. That's the first conclusion. Next, let's explore U star large. So actually I can just move this down here. So I'm assuming that both of them are large. So here I have that U star is equal to alpha over 1 plus V star squared, and that implies that U star is approximately equal to alpha over V star squared, and there's a similar equation, V star is equal to alpha over U star squared. So I can substitute. Let me call this star. Maybe that's bad notation, and this is double star. So I'm going to substitute double star into single star. And that tells me that u star is equal to alpha over alpha squared times u star to the fourth power, which implies that u star is alpha to the 1/3. And ditto, v star is alpha to the 1/3 by the same argument. Last, let's see if there are any solutions for u star and v star both small. So we found basically three solutions, but what about u star and v star both small? And so, you would have u star is alpha over 1 plus v star squared, and that's so that gives me that u star is approximately equal to alpha, and that contradicts our assumption about both of them being small. Okay, maybe we'll explore that a little bit more in the homework. Now, what about the case where alpha is much, much less than 1? In this case, let me just review what I had written down for myself. So let me look at the case where I'll consider u star much, much less than 1. So I have that v star is equal to alpha over 1 plus u star squared, and so this thing, because u star is by assumption much, much less than 1, this gives us v star is approximately equal to alpha. And now I can solve for u star, which is equal to alpha over 1 plus v star squared, which gives me u star is approximately equal to alpha as well. Is this what I wanted to say? Yeah, so that's fine. That's a reasonable outcome in this case. And by the way, that corresponds to this fixed point, which we didn't talk about much the other day, but we would only find one fixed point in the case where alpha is much, much less than 1, and so we see that both u and v are small. Let's see whether there's, now let's consider u star big, and see where that leads us. So v star is equal to alpha over 1 plus u star squared, and that's going to give us alpha over u star squared, roughly. That's fine. Now let's see what happens with u star. U star is going to be alpha over 1 plus alpha squared over, wait, what happened here? I think I'm getting myself confused, just bear with me, sorry. So what do I want to say? Well, okay, so let's see here. So first of all, what we've done is we've assumed that u star is much, much greater than 1. And we use that to compute v star, which is equal to alpha over u star squared, which is thus really, it's really small, because we've already said that alpha is itself small. So V star is very small. And now this gives us here that this is approximately equal to alpha. And so what we've found is a contradiction, because here we find that U star on these by following the path of assuming that U star is big, that led us to this result. And then when we compute U star, what we find is that it's of order alpha, which is small. That's a contradiction. So let me just try to summarize. I hope that wasn't, this is a bit technical, but so what I was trying to do is just get a feeling for the nature of the fixed points. And just as a reminder, we put the equations in dimensionless form, which I'll circle them here. So that's the dimensionless form of our equations. And then I said, well, let's explore the fixed points. What I mean by that is du by d tau is 0 and dv by d tau is 0. So that gave us some conditions. We assumed here that alpha was very big. This is the cooperative limit, if you like. And then we explored. We said, well, let's think about what happens if U star is very small. And that led us to a V star, which is of order alpha. That's nice. So that's large. And then we self-consistently went back and found what U star would be, and we found that that's 1 over alpha. And by symmetry, we had U star as alpha, and V star as 1 over alpha, and vice versa. We have U star as alpha, and V star as 1 over alpha. So those were our two wings, the switching points. Then we said, well, let's assume that U star is large, and so, or I should say, I assume that both of them are large, U star and V star. I plug into these equations, and what I find is U star is of order alpha over V star squared, V star is of order alpha over U star squared, and by substitution, I found both U star and V star are alpha to the 1/3, which is that fixed point in the middle, which is kind of this intermediate value, and later we'll see that that's the unstable fixed point. And then basically we looked at the alpha small case, and we found one solution, which is U star equals V star, both of them small. And we were unable to unearth any other solutions. So that's basically the landscape of these fixed points in terms of parameters. I did it in dimensionless form, but now you can see what they are in terms of their parameters. And this poises us to now be able to do what I will refer to as the linear stability analysis.